Hi, everybody, and welcome to Week 2, Day 5, Mysteries. Today, we're going to talk about consciousness and ethics in the context of neuro-AI. I'm your host, Megan Peters. I'm an associate professor of cognitive sciences here at the University of California, Irvine. I'm director of the Cognitive and Neurocomputation Lab here at UCI. I'm a fellow in the Center for the Neurobiology of Learning and Memory, also here at UCI, and a fellow in the Canadian Institute for Advanced Research, Brain, Mind, and Consciousness program. And for those of you who have taken several of our other courses here at NeuroMatch, you might also recognize me as I'm one of the co-founders. I'm the president and chair of the board right here at NeuroMatch. So today, we get to talk about what I think are some of the most exciting aspects of this entire field: the unsolved mysteries. So as AI gets smarter, it becomes more able to behave in seemingly intelligent ways. It's able to generalize better, which is a main theme of this course. Maybe you think it's going to wake up. Has it already woken up? What would it mean scientifically, ethically, and morally if an AI were to become conscious? Does it matter whether it's conscious for other ethical considerations like moral status? And how can we make safe, ethical, and responsible AI? And how can we be responsible in building artificial intelligence? More specifically, here are today's topics. First, we're going to talk about consciousness, what it means, how it might arise from brains. We're also going to explore programming some agents that might have some key properties we think are associated with consciousness. And then we're going to ask, are those AIs that we have now just built actually conscious? And then we're going to turn to ethics. We'll talk about the moral status of natural and artificial agents. We'll talk about ethical treatment of and by artificial agents. And then we'll talk about the ethical use of neuro-AI, or AI in general. So today's activities look a little bit different from the previous days in this course. Of course, we'll do a little bit of coding. So we'll have our traditional Python notebooks, we'll have our micro lectures, we'll do some peer programming. So this will look an awful lot like the same as usual. This will include programming some models that might have the seeds of consciousness, although maybe you'll be a little skeptical. But we're also going to supplement the traditional coding exercise with some guided discussions. And the format of these is that you'll have a discussion prompt. You might also be asked a specific question. And then we'll go into breakout rooms where you can choose the answer to your question or the question you'd like to discuss. And then you'll come back from those breakout rooms to share thoughts among your whole pod. So these questions might take the form of things like, does something count as actual consciousness? Or how can we ensure we're building ethical, moral, or good artificial intelligence? We also have some bonus content in both the code and the discussions. If you don't have time to get to everything today, you can pick and choose as a group or come back to some of these later on your own. So we invite you to choose your own adventure, so to speak, and have fun exploring. We're going to be joined today by a whole cast of experts on this field. So in addition to myself, Megan Peters, we'll also have Joe Ledoux, Matthias Michel, Dan Dennett, Haquan Lau, Steve Fleming, Guillaume Dumas, Claire Sargent, Anil Seth, Josh Shepard, and Jana Schachborg. And we also would like to acknowledge that the funding for today's materials has been provided by the Canadian Institute for Advanced Research. And today's message also looks a little different. In particular, it's because today's message is about the unsolved mysteries, not the solved ones. And consciousness and neuroethics are truly unsolved. We don't know the right answer to a lot of the questions and content that we'll be discussing today. Not yet, anyway, but hopefully in the near future, you'll get to contribute. So what we're going to do today is get lots of different viewpoints. We're going to explore the terminology, ideas, and challenges we face when trying to understand consciousness from a scientific perspective, and when trying to work through the ethics of building responsible AI, whether it's brain-inspired or not. So all those experts' names that I showed you a few slides ago are going to join us. So together we can explore the state of the art in the field, and also how much further we all have to go together. And one thing you'll note is that they do not always agree with each other. We thought that it was really important to show you all how diverse the expert opinions are in this field right now, not just tell you that these challenges are unsolved. So your task for today is to exercise your critical thinking. There is no right answer in consciousness science or in the ethics of artificial intelligence. But after today, we think that you're going to be better equipped to weigh in on these controversies and help push the field forward in meaningful and really exciting ways. So here we go. Let's first spend a little time here in the introduction lecture giving you some foundations for the consciousness tutorials. So let's start with some definitions. Perhaps you've noticed that when people talk about artificial consciousness, there are many different terms that get used. Sometimes it seems like people use these terms interchangeably. So for example, there's a lot of talk right now in the media and around the world about the breakneck pace of AI development. Artificial general intelligence, conscious AI, AI that might achieve sentience, the singularity and the threat of AI with motivations and goals that are at odds with human survival. Are all of these the same thing? Is consciousness the same thing as intelligence and self-motivation? Let's use a concrete example. Fear, the feeling of being afraid. When you're afraid, you feel fearful, but you also exhibit all sorts of behavioral signatures of fear, especially if you're a mouse. Faced with a predator looming over you, you freeze, or maybe you run away or you hide. But are these behaviors, freezing or running or hiding, the same as the feeling of fear? To make it even more clear, if I create a new drug or treatment that reduces the behavior of freezing, running away, and hiding in mice, can I conclude that it's making the mice feel less afraid? Can I conclude that the drug will make humans feel like they're less afraid or less anxious? This is the model used by a lot of behavioral and pharmacological research, because, of course, you can't ask a mouse how it feels. You can only measure its behavior. But as we'll see in this section, drawing a direct link between feelings and behavior isn't straightforward. So to help us understand this, let's hear first from Joe Ledoux, professor of neuroscience and much more at New York University. He's going to tell us about the important distinction between the subjective feeling of fear and the behavioral signatures of fear.
Because we humans feel afraid when in danger, we tend to believe that the feeling of fear is what causes us to defend ourselves by freezing or fleeing. This is a conflation of causation with a correlation. Fearful feelings and defensive behaviors are controlled in parallel in the brain. Defensive reactions are evolutionarily ancient responses that are triggered by innate or learned dangers. Human fear, on the other hand, results from the cognitive interpretation of a situation as dangerous, based on memories, especially schema, about what fear is and its relation to danger. Fear is individualized by your experiences, which are contextualized by your culture. Danger, not fear, is universal around the world. Medications to treat fear and anxiety developed by measuring defensive behaviors in animals can be useful in controlling behavioral and physiological symptoms, but cannot ameliorate the subjective anguish that defines fear and anxiety disorders.
So we're beginning to see that this distinction between the feeling of something and the behavioral signature of that thing is really important and really difficult. Next, we're going to hear from Matthias Michel, assistant professor of philosophy at the Massachusetts Institute of Technology, for a more zoomed-out version of this idea.
One of the most important shifts in the history of ideas was the discovery that complex mental processes like reasoning, perception, or learning can occur unconsciously. For instance, you might have had the experience of failing to solve a difficult problem, only for the solution to later suddenly pop into your mind, seemingly out of nowhere. What happens in this case is an instance of unconscious reasoning. You solved your problem unconsciously. And what this shows is that the mind can engage in intelligent mental processes without consciousness. This means that an animal or an AI system might behave in seemingly intelligent ways without necessarily having conscious experiences. In the words of the philosopher Ned Block, we have to distinguish between cognitive access and phenomenal consciousness. Cognitive access grants you intelligence. It's the availability of information for rational decision-making. Meanwhile, phenomenal consciousness is subjective experience. It's the fact that there is something it's like for you to perceive, to have emotions, to think, and so on. When phenomenal consciousness is there, the lights are on, so to speak. Now, this distinction is crucial because it makes it clear that you could have conscious experiences, phenomenal consciousness without cognitive access, or cognitive access without phenomenal consciousness, intelligence without subjective experience.
So, what Joe and Matthias have now shown us is that there is an incredibly important distinction between phenomenology, or the qualitative feeling associated with a mental representation or information processing, and global availability of information for processing, behavior, intelligence, and so on, or even the neural activity itself. In the words of philosopher Tom Nagel, we're talking about the subjective, qualitative nature of an experience. He says, fundamentally, an organism has conscious mental states if and only if there is something that it is like to be that organism, something it is like for the organism. We may call this the subjective character of experience. So what this means is, if an entity is conscious, someone's in there, the lights are on, the AI, or any other entity, has woken up. And importantly, this means that qualitative phenomenal experience seems to be made of a different kind of stuff than neural biochemical activity or even neural representations as informational constructs. So now we have a challenge. How can we even study the qualitative experience aspect of consciousness? But maybe more importantly, how can we use any study of behavior or neuroscience at all to study consciousness? Consciousness seems to be fundamentally a totally different kind of thing. In fact, the gap between qualitative phenomenal experience and neural or biochemical activity seems so large that figuring out the relationship between them has been called the hard problem by philosopher Dave Chalmers. He says this gap is maybe insurmountable. Even when we have explained the performance of all of the cognitive and behavioral functions in the vicinity of experience, perceptual discrimination, categorization, internal access, verbal report, there may still remain a further unanswered question. Why is the performance of these functions accompanied by experience? So, are we doomed? Even if we completely understand a brain or we build an AI system that we completely understand, maybe we still won't be able to know anything about the qualitative nature of experience at all. Maybe. But let's hear now what another philosopher has to say about the hard problem for an alternative viewpoint. We are very fortunate now to be hearing from Dan Dennett, considered during his life to be one of the most widely read and debated American philosophers, and often spoken about in the company of Richard Dawkins, Sam Harris, and Christopher Hitchens. He was also formerly the co-director of the Center for Cognitive Studies and professor of philosophy at Tufts University, and a profoundly influential thinker in the fields of cognitive science, philosophy of science, and philosophy of mind. Having Dan with us here at NeuroMatch to talk about consciousness is also very special because he passed away less than 2 weeks after he recorded this video for us. So I hope you'll all listen closely as Dan walks us through an alternative viewpoint on the hard problem of consciousness.
Hello, I'm Daniel Dennett, and I'm going to try now to share my screen so I can say a little bit to you about the hard problem. So here we go. Here's a philosophical error that David Chalmers made some years ago. He asks, why is it that when our cognitive systems engage in visual and auditory information processing, we have visual or auditory experience, the quality of deep blue, the sensation of middle C. Why should physical processing give rise to enrich inner life at all? And then Ned Block, another philosopher, picks this up and talks about phenomenal consciousness or P consciousness. And he says, P conscious states are experiential. That is, a state is P conscious if it has experiential properties. The totality of the experiential properties of a state are what it is like to have it. Well now, do brain states have experiential properties, or do they represent experiential properties, or is it a little of both? Here's a comically naive idea. Compare an old-fashioned cinema film to a DVD or any digital video file. The film represents red by having red pigment on each frame wherever there's a red thing. The digital file represents red by having zeros and ones in various positions, or micro dots, or whatever you want. But the point is that representation of red in a DVD or a digital file is not the same as representation of red in an old-fashioned cinema film. And this is, I think, the mistake that Block and Chalmers are making. They're supposing that in order for the brain to represent colors and odors and everything, it has to have phenomenal properties. But just what does that mean? Representation in the brain is not like old-fashioned cinema representation. It's also not like representation on the DVD, but that doesn't mean that it uses little dots of pigment anywhere in it. I want to make this problem seem especially vivid to you. I want you all just to stare at this yellow, black, and green flag, and we're going to stare at it for a few more seconds, a few more seconds, a few more seconds. That should be long enough. Stare at the cross. Don't look anywhere else. Okay? Now, what do you see? Do you see the red stripes? Do you see the blue rectangle? Now, here's what I want to ask. Those red stripes, where are they? And what properties do they have? They're not on the screen, right? And in fact, they're not on your retina either. Well, you might say they must be in my mind. Stop. You don't know that. You don't know how it is that you seem to see those red stripes. They don't seem to be behind your eyes. They seem to be out in front, right? When you close your eyes and imagine a red stripe, it doesn't seem to be inside, or if it does, it doesn't make any difference. The point I'm trying to make is that the representation of a red stripe isn't red in your brain. And since it isn't red, it isn't phenomenal red, and we can get rid of the philosopher's term qualia altogether. No doubt there is a medium of representation in your brain, but that your access to that medium is underprivileged. You don't know much about it at all. We don't know much about it at all. You know almost nothing about the properties of those media. But one of its functional properties is putting you in a state of believing you're seeing a red stripe. That's the property that matters, the functional property of putting you in the state of believing that you see a red stripe. But now, what is the difference between just idly thinking that there are red stripes and thinking that you're seeing something red right now? Nick Humphrey's answer is sensation, something that he says only birds and mammals enjoy. I am not entirely convinced of this, but I think he's right about something. That was in his book Sentience. It came out just last year. which I'll try to describe. So here's another little thought experiment. Close your eyes and imagine as vividly as you can that somebody wearing steel-toe boots kicks you in the left shin as hard as he can. Imagine it now. Ooh. Did any of you feel any pain? Do I need to apologize to anyone for causing them suffering? No, I don't. Imagining pain is not the same phenomenon as feeling pain. And imagining red is not the same phenomenon as seeing red. Imagining a red stripe is not the same phenomenon as believing that you are seeing a red stripe now. What's the difference? Is it qualia? No, there are other functional properties that state has, and that is what you have to turn to instead of making the mistake of thinking there's something like pigment in the brain. What's the difference? There are indefinitely many sequelae to seeing an illusory red stripe, but no rendering of red. There is nothing red in your brain that is responsible for your seeing or imagining or seeming to see or believing that you're seeing a red stripe. The last red stripe is actually on your retina, but that's not what you're seeing. I'm going to end this very brief discussion by telling you about a card trick, which I think is to the point. This is a card trick done by a famous magician of many years ago named Ralph Hall. And this was the trick he did for his fellow magicians, which is very unusual. I'm going to give you a sense of how it runs. He says, boys, here I'm going to stop the screen share. He says, boys, I've got a tuned deck. I listen to the deck, buzz, buzz, buzz. I can hear the tuning, and I can get the card to come out because of the fine tuning of the deck. And then he fans out the cards, and he says, okay, pick a card, any card. And they pick a card. And they put it back in the deck, and he goes buzz, 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 and he produces the card. And he says, now, how did I do it? And his fellow magicians are all stumped. Well, you know, they have some ideas. Maybe, I'm not going to tell you too much card magic. Maybe they say, maybe he's doing an A-type trick. I won't tell you what an A-type trick is. So they know how to prevent him from doing an A-type trick. Well, maybe he's doing a B-type trick. No, they prevent him from doing that, and he still does the trick. Now, Hull is breaking every rule of good stage magic. You don't ever do a trick twice. But he did. He made a point of it. He did it for his fellow magicians, and he did it as long as they wanted to play. And they never got it. They tried to buy the trick from him. They gave up. Then he explained it in a wonderful book. Hilliard's book, Greater Card Magic, if you want to know. And here's the trick. As he said, the boys were all looking for something too hard. The trick in its entirety is in the name of the trick, the tuned deck. And in fact, it's in the first word, the. He said, I've got a new trick. It's called the tuned deck. Trick's over. Now he does an A-type trick. He said all the buzz stuff is obviously nothing. And so they prevent him from doing an A-type trick. So I think maybe it's a B-type trick. They prevent him from doing that. So he does a C-type trick. Maybe it's a C-type trick. So they prevent him from doing a C-type trick. He goes back to doing an A-type trick. He's just going round and round. They think they've refuted the hypothesis that it's an A-type trick, a B-type trick, a C-type trick. They were all looking for something too hard. And I think that's the mistake that people make when they fall for the hard problem. David Chalmers' hard problem is an example of the tuned deck. In effect, David Chalmers is saying, boys and girls, I've got a new problem. It's called the hard. And he hasn't proven that there's a hard problem. There's all the so-called easy problems. Those are actually the hard problems. What we want to do is set aside the hard problem, which is just a magician's fantasy, and concentrate on the really hard question. And then what happens? What happens in the brain? How are colors and aromas and sounds and so forth represented in the brain? And they're not represented by colors and aromas and sounds. They're represented by neural activity of one sort or another. So that's my little message for the day. I hope you like it.
So the hard problem may seem compelling to some, but others think it's not a problem at all. That is, maybe we don't need to find the rendering of red or other qualitative experiences in the brain. We need to find functional properties, consequences of seeing red, representations that go with seeing red. And finding those representations of qualitative experience is enough. We don't need qualitative experience on top. And furthermore, Dan argues, it's hard enough to find neural representations and functions, the so-called easy problems, without needing to posit the hard problem of consciousness as well. So keep this all in mind, both Dave Chalmers' hard problem and Dan Dennett's assertion that it isn't, in fact, a problem, because it's going to come back in the coding exercises and discussions that we'll do in a bit. So this is the first taste of the controversial nature of this field. Scientists and philosophers tend to disagree a lot with each other, within and across these perspectives. And they disagree about how best to study consciousness and what we think we may have learned from empirical studies. But I think we can mostly agree on one thing. Intelligence can exist without consciousness, without someone being in there, or without there being something that it's like to be that intelligent entity. An amazing amount of sophisticated processing can take place without consciousness. You've learned about some of them in this course, in fact. And the other way around can be true too. We can easily conceive of an entity that possesses consciousness but isn't very intelligent. Maybe there's something that it is like, some qualitative experience associated with being a mouse, but you won't find a mouse playing chess anytime soon. In other words, intelligence and consciousness are not the same thing. Next, let's talk a little bit about how consciousness is studied from a scientific perspective. These examples will also help you understand the coding exercises we'll do in the first tutorial and some of the discussions you'll have after you do all that coding. So how do we study consciousness in the lab? The primary goal of many experiments is to isolate the neural correlates or computations that specifically are associated with consciousness and not associated with general automatic processing of some stimulus. So, for example, you'll have a human observer in your experiment, and on every trial of some task, you show this observer a light that's turned off or turned on. You ask the observer to report whether they saw the light or not on every trial. You assume that most of the time when the light is off, they say no, and when it's on, they say yes. Is this a good test for whether the human is conscious of the light? If you think yes, what happens now when I replace the human observer with a light sensor in a camera that's hooked up to some very simple output or report system? The light sensor should also be very good at detecting whether the light is on or off, and also say no when it's off and yes when it's on. Is the light sensor conscious? I would think not. So the challenge for studying consciousness in the lab is to create conditions where automatic, presumably unconscious processing is held constant, and we just manipulate whether the observer is actually subjectively aware of the stimulus. A striking example of this that occurs naturally, although very rarely, is the neurological condition of blind sight. In some rare patients, damage to primary visual cortex results in a condition where patients report having no conscious visual experience at all, and yet they can actually process visual information in a task effectively. They can tell whether that light bulb is on or off to some reasonable degree, but when you say, "Did you consciously see the light?" they say, "No, I'm blind. I can't see." This condition was first reported by Larry Weiskrantz and colleagues back in 1974, and since then there have been a handful of patients worldwide. The condition has also been created in monkeys as well through lesion studies. This video shows us exactly what this is like. The man in the video claims to have no conscious visual experiences at all, and yet, when prompted, is able to navigate this hallway and successfully avoid obstacles. So what we need to try to do is create conditions in the lab that also create meaningful processing in the brain, while turning off or manipulating the amount of conscious awareness of stimuli. Typical experimental manipulations to do this include visual masking, continuous flash suppression, transcranial magnetic stimulation, very dim or low contrast stimuli, and so on. So to wrap up this discussion, what is the difference between blind sight and normal low vision? The answer is phenomenal consciousness. But how does the brain do this? What is it about the brain's hardware or activity or something else that generates experiences that have phenomenal character? Experiences that have something that it's like to have those experiences? The answer to this one is we actually don't know yet. But we have a few ideas, and we have a few theories. So in the next sections and the tutorials that you'll do following that, we'll talk about some of the theories of consciousness and get to program some toys that exhibit some of the computational properties that these theories think might be involved. The last part of this introductory video is meant to give you an overview of some of the current theories of consciousness. There are a number of theories of how consciousness might be generated or supported in the brain, or in an agent that has a brain and a body. In this paper, published in 2022, the authors reviewed some of the ones that are discussed most in the literature. They put them into these categories, some of which have one theory in them and some of which have many, a family of theories clustered around a similar theme. These include recurrent theories, predictive processing theories, higher order theories, global workspace theories, and integrated information theory. Some of these theories assume that performing computations of the right kind is both necessary and sufficient for consciousness. So according to those, consciousness in AI is possible in principle if AI were to exhibit all of the right kind of computations. But what do the right kind of computations look like? It turns out they're different for every theory. So let's do a very quick overview of some of these theories, and then we'll dive much deeper into just a very few of them in the coding tutorials coming up next. The first of these is recurrent processing theory. These theories say that recurrent processing is both necessary and sufficient for consciousness. This includes feedback in addition to feed-forward activity. The idea is that algorithmic recurrence is used to generate integrated perceptual representations, such as organized and coherent scenes, figure-ground segregation, objects, spatial relations, and more. Predictive processing theories instead say that the essence of human and animal cognition is the minimization of errors made by a hierarchical generative model that predicts sensory stimulation. In perception, this would look like the case where a model continuously generates predictions at multiple levels, which are influenced by predictions at neighboring levels and in the immediate past, as well as prediction error signals from sensory stimulation itself. This whole process is also modulated by attention, and according to the theory of active inference, can also control action, since acting can end up reducing prediction error. What this means is that adaptive actions would be selected if an organism predicts its own success. It's worth noting that this isn't strictly a theory of consciousness. It's more like a theory of cognition, a more general framework. So this is a paradigm in which theories of consciousness could be developed. Global workspace theories posit that brains and minds have specialized systems which can perform tasks in parallel. These can be thought of as modules, but they don't need to be informationally encapsulated or use dedicated components. These theories also posit that there is a bottleneck of information flow, that the workspace capacity is smaller than the collective capacity of all of the modules put together. This ends up forcing the system to learn useful, low-dimensional, and multimodal representations. The idea then is that information in this workspace is globally broadcast, made available to all of the modules, meaning that the modules themselves also take inputs from the global workspace. There's also a selection mechanism, which determines the information that will be sent into the global workspace from the modules. This selection mechanism must be sensitive to the system state and any new inputs received. What this means is that the modules and the selection mechanism need to engage both top-down attention and bottom-up attention. This will allow representations in the workspace or in the modules to affect which information is selected from each of the modules. The family of higher-order theories, which includes several different variants, goes like this. The perceptual reality monitoring variant posits that perceptual states are conscious when a metacognitive monitoring mechanism identifies them as being reliable or accurate states of reality. The higher-order state space variant posits that consciousness depends on higher-order awareness states, which are directed at first-order perceptual representations. The linking factor here is that in higher-order theories, the person or system as a whole takes perceptual contents that are labeled as real to be actually real. And this requires that the system is an agent that can possess beliefs of this kind. So how would we program these computations into a model? In the first tutorials today, you're going to hear from some experts on several theories for a much deeper dive into a few of them. And you'll also get to work with some simulations. You'll also engage in some discussions about what this all means. Have fun!